C++ is not disappearing. Something more important is happening. For decades, when a company needed software that was fast, close to the hardware, and free from a garbage collector, C++ was the obvious choice. Google used it in Android. Microsoft built large parts of Windows with it. Amazon relied on it throughout AWS infrastructure. Those companies still run enormous amounts of C++ today. They are not deleting it overnight. But when their engineers start certain kinds of new systems, especially code that processes untrusted data or runs with deep access to a machine, C++ no longer wins automatically. Rust is taking that decision. This distinction matters because programming languages rarely die through mass deletion. They lose when new projects stop choosing them. Google is writing new Android components in Rust. Microsoft has Rust running inside the Windows kernel and is building official support for Rust drivers. Amazon uses Rust in Firecracker, BottleRocket, and parts of the infrastructure behind major AWS services. 3 companies, 3 different migration strategies, one shared conclusion. They still need C++ performance. They no longer want to accept every C++ risk that comes with it. So is Rust replacing C++? Not line by line. It is replacing C++ at the moment when an engineer opens an empty project and asks, what should we build this in? C++ gives developers enormous control. You can decide where data lives, when memory is allocated, when it is released, and how closely the program maps to the hardware. That control is why C++ became foundational to operating systems, browsers, game engines, databases, trading systems, and embedded software. It is also where the security problem begins. C++ trusts programmers to manage memory correctly. A program can read outside a buffer, use an object after it has been freed, or corrupt memory through a pointer mistake. The code may compile successfully, it may pass tests, it may run in production for years before one unusual input exposes the error. Companies have spent decades trying to catch these mistakes. They use code review, fuzz testing, sanitizers, static analysis, hardened allocators, sandboxing, and exploit mitigations. All of those tools help. None changes the language's basic agreement with the programmer. C++ often says, I will let you do this. You are responsible for making sure it is safe. Rust changes that agreement. Its ownership and borrowing rules allow the compiler to reject many memory errors before the program runs. Developers can still write unsafe Rust when they need low-level access, but that code has to be marked explicitly. The argument for Rust is not that its developers are more careful. It is that carefulness should not be the only barrier between a mistake and a security incident. That is why big tech's adoption of Rust is less about language taste than risk management. Each company is asking the same question: how much dangerous freedom does this component truly need? Google's Android strategy is easy to misunderstand. Google did not decide to rewrite Android in Rust. Android contains a huge amount of existing C and C++ code. Replacing all of it would take years, create compatibility problems, and introduce new bugs along the way. Google chose a less dramatic approach. It concentrated on new code. The reasoning was simple. New code creates a steady supply of new vulnerabilities. Older code that has survived years of use generally produces fewer new discoveries than code that is still changing quickly. If Google could write new native Android components in memory-safe languages, the flow of new memory bugs should begin to shrink. That is what happened. In 2019, memory safety issues accounted for 76% of Android vulnerabilities. By 2024, that figure had fallen to 24%. Google's 2025 data placed it below 20% for the first time. Google also reported a roughly 1,000-fold difference in memory vulnerability density between Android's Rust code and its C and C++ code. Then came the result that may matter even more to engineering managers. The Rust changes were not merely safer. Google reported that they had 4 times fewer rollbacks and spent 25% less time in code review. That attacks one of the most common objections to safer languages, that safety must slow development. Inside Android, Google found the opposite. The compiler created friction while the engineer was writing the code, but less trouble escaped into review, release, and production. Google's strategy is not rewrite everything. It is stop adding to the most expensive category of risk. Existing C++ can remain where replacing it makes no economic sense. Rust gets the new components, the exposed components, and the code where one memory error could cross a security boundary. Over time, the dangerous part of the codebase becomes older and smaller without requiring a heroic rewrite. Microsoft approached the problem through some of its most sensitive software. A normal application crash is annoying. A memory error inside the operating system kernel can be far worse. Kernel code runs with privileges that ordinary applications do not have. A bug there can affect the security and stability of the entire machine. Microsoft now ships Rust inside the Windows kernel. Windows 11 version 24H2 includes a Rust implementation of GDI regions in a kernel component called Win32kbase-RST, sys. Microsoft's own documentation says users should expect more Rust in the kernel because of its reliability and security advantages over C and C++. Azure has been equally direct about its direction. Microsoft has described Rust as its preferred alternative to C and C++ for systems where garbage-collected languages do not fit. It has already adopted Rust in security-sensitive Azure infrastructure and expects that use to grow. The next step is bigger than Microsoft's internal code. The Windows team is working to make Rust a first-class option for driver developers. Its tooling can already build Rust drivers that load and run on Windows 11. The work is not finished. Many Windows interfaces still require unsafe Rust because the operating system APIs were designed around C. Microsoft is developing safer wrappers, but wrapping decades of kernel interfaces takes time. That limitation reveals something important. Choosing Rust does not magically make every layer safe. When Rust crosses into old C interfaces, someone still has to define the boundary correctly. Microsoft is not replacing the Windows codebase with pure Rust. It is creating safe zones inside a system built long before Rust existed, then widening those zones as the tooling matures. That is slower than a clean rewrite. It is also far more realistic. Amazon's story looks different because several of its best-known Rust projects began as new infrastructure rather than language migrations. Firecracker is one example. AWS released Firecracker publicly in 2018. It is the virtualization technology used to create the lightweight micro-VMs behind services, including AWS Lambda. A virtual machine monitor is exactly where a memory error becomes frightening. It sits close to the boundary between customer workloads and the underlying host. AWS wanted the speed and low-level control associated with C and C++. It also wanted stronger memory and thread safety. Rust offered both. Amazon later launched Bottlerocket, a Linux-based operating system designed specifically for running containers. Large parts of Bottlerocket are written in Rust. AWS has also used Rust in services and infrastructure connected to S3, EC2, CloudFront, Route 53, and the Nitro system. The ECT2 team has called Rust its language of choice for new Nitro components, including security-sensitive applications such as Nitro enclaves. Amazon's pattern is clear. It is not searching through every AWS service for C++ to remove. It is choosing Rust when it builds new infrastructure that must be fast, predictable, and difficult to exploit. That gives Amazon an advantage Google and Microsoft do not always have. A new system has fewer compatibility constraints. The team can design its interfaces around Rust instead of forcing Rust through decades of C and C++ assumptions. This may be where Rust replaces C++ fastest, new infrastructure with a high cost of failure and no existing C++ codebase to protect. Google, Microsoft, and Amazon are not following one master plan. Google is reducing the inflow of memory-unsafe code. It keeps much of Android's older C++ while steering new native development toward Rust and other memory-safe languages. Microsoft is introducing Rust into a mature operating system and cloud platform. It is starting with sensitive components, kernel code, firmware, and driver tooling. Amazon often uses Rust for new infrastructure. Firecracker and Bottlerocket could begin with memory safety as a design constraint rather than acquire it later. These strategies fit three different situations. If the existing codebase is enormous, change the language used for new code. If the system cannot be rewritten, isolate risky components and replace them gradually. If the project is new, choose the safer foundation before legacy decisions harden around it. None of these companies treats Rust as a universal replacement for every language. Google still invests heavily in C++ tooling and interoperability. Windows will depend on C and C++ for a very long time. AWS runs services written in many languages because infrastructure, control planes, business services, and user interfaces have different requirements. The common choice is narrower. When performance matters, garbage collection is undesirable, and memory corruption creates serious security risk. Rust has become a credible default. 10 years ago, C++ often entered that conversation alone. It does not anymore. Rust solves an important class of problems. It also creates its own costs. The ownership model takes time to learn. The borrow checker can feel hostile when developers first encounter it. Some designs that are natural in C++ need to be reorganized before Rust will accept them. Compilation can be slow. The library ecosystem is younger. Certain hardware platforms and specialist industries still have better C++ support. C++ also has decades of mature tooling, engineers, libraries, debuggers, and institutional knowledge behind it. A game studio with a large C++ engine cannot move because another language has better safety guarantees on paper. Its rendering code, asset pipeline, editor tools, console integrations, and developers may all depend on the current ecosystem. There is also the uncomfortable part of Rust that enthusiastic explanations often skip. Rust programs can contain unsafe code. Operating systems, drivers, and hardware interfaces frequently need it. A bad, unsafe abstraction can undermine the safe code built on top of it. Rust reduces the amount of code that requires manual memory reasoning. It does not abolish that reasoning. And language choice cannot fix bad authentication, exposed credentials, broken access control, incorrect business logic, or a careless deployment. Memory safety is a large security problem. It is not the only security problem. This is why Rust good, C++ bad is an unserious conclusion. C++ remains an excellent tool when a team understands its risks, has the right expertise, depends on its ecosystem, or cannot justify a migration. The economic question matters as much as the technical one. Will replacing this component prevent enough future damage to justify the rewrite? Sometimes the answer is yes. Often, the best answer is to leave the old C++ alone and write the next component in Rust. Rust is replacing part of C++. It is taking new systems code where security matters, performance must remain high, and companies no longer want memory safety to depend entirely on developer discipline. Google's Android results show that changing new code can reduce vulnerabilities without rewriting the old platform. Microsoft shows that Rust can enter a mature operating system one component at a time. Amazon shows what happens when Rust becomes the foundation of new cloud infrastructure from the beginning. But none of these companies has proved that C++ is finished. Their decisions point to a more precise conclusion. C++ is moving from automatic choice to justified choice. A team starting a new security-sensitive component now has to explain why it needs C++ instead of Rust. That conversation barely existed a decade ago. Billions of lines of C++ will continue running for decades. Companies will maintain them, improve them, and pay experienced engineers well to understand them. Rust does not need to erase those lines to win. It only needs to keep taking the next project. So the most useful answer is also the one most likely to annoy both sides. Rust will not replace C++ everywhere. It is replacing the assumption that serious systems software must begin with C++. Which side would you choose for a new operating system component today? And what would have to be true for you to choose the other one?